Okay, so in preparation for today's class, I said that people should see the advanced cache optimizations video. So I'm expecting it to be interactive where you ask questions and answer. So, as I said in the last class as well as in the message I sent to Bansi, some of the techniques are what we had already covered and some were more advanced optimizations in that video. So I want to hear feedback from you about that video.
Ma'am,
Yeah.
videos were very good, ma'am. But I didn't understand pipeline cache very much, ma'am. So can you explain that once more?
Yeah. Okay. Because I'm asking for feedback because I have to make decisions about what videos I'll use in the class later also. He has a whole lot of videos. Now I have put up the entire course link on the our course page. I don't know if any of you have seen that. So if there are no questions about what has been covered in that video, I'll only cover what has not been covered in that video, right? In fact, if you look at Bhaskaran Raman's third video, which is cache performance video, and this video, I think they cover almost everything in advanced cache optimizations. So last time we looked at these two, that you reduce the hit time by using small and simple burst level caches and wave prediction, right? And I think the wave prediction is very nicely explained in that video. So did this come in the video, the early restart and critical word first? I remember that it was there in Bhaskaran Raman's video. Don't remember if it was there in this Georgia Tech video. Any questions about this? Because it's a very simple mechanism to improve the miss penalty. Okay, merging write buffers. I don't remember seeing this in any of them. Could be wrong, but let me just talk about this because if you look at the first figure in this slide, we are trying to write to addresses 100, 108, 116 and 124. Now the write buffer can hold a 64-bit, supposing it can hold 4 8-byte quantities. It's like a wide word, okay? So each row of the write buffer can hold 4, um, 4 of the 8-byte quantities, and it has 4 such rows. So overall it can hold 16 8-byte words. Supposing it is that, then when we try to write to addresses 100, 108, 116, 124 and so on, we are essentially using different rows and adding, indexing into those different rows and writing them into those memory words. Now the problem is that these memory words, um, it's like a way, right? 4 ways sort of a thing. And as you can see, the valid bits are there, whether they are valid or not. And what did we do in the lower image? Basically, because the addresses are all contiguous, we have put them into the different ways of the same indexed location. Because they form a contiguous block, 100 to 120, 132 bytes. It's a contiguous block that they form. So when you have such contiguous addresses, you can merge the entries of the write buffer so that you can actually release more space in the write buffer and do a write back fewer number of times. Okay, so therefore your miss penalty will be reduced because instead of writing now, the write back from the previous figure, which would take 4 write backs, okay, because it puts the 4 different addresses 4 times on the address bus. Instead of that, it puts one single address 100 on the address bus and it can say I'm writing 32 bytes. Then it can simply send the 32 bytes and they'll be written in contiguous locations. So it helps to reduce miss penalty because of that also. Oh, my audio is bad. That's what is it? Rukma ma'am says I'm not audible.
Yeah. Now it's fine, I guess. In between somewhere,
Okay.
there was a lot of
Anyway,
silence.
I think comparatively, in the beginning, I remember never had problem with Zoom, but nowadays to get on to this meeting, it takes me some time, at 2-3 attempts, then only I get in. And probably even, so let me just repeat what I said in case, I had been lost. The addresses here are contiguous addresses. So you can actually merge the entries into a single index, okay, and into 4 ways. And when you do a write back, you can put one single address on the address bus and write contiguous memory. So, obviously it takes time if you have to say, I'll put this address, write few bytes, then another address, then write few bytes. The amount of penalty that you have to pay for that versus you put the address once and write contiguous number of bytes, the penalty will be reduced. So that is one thing. And the second thing is that the write buffer now, if you look at the contrast between the top and lower images, the top image is according to, even though 3/4 of the buffer is free, there are no more entries to index into the write buffer. Therefore, it cannot actually, accommodate any more entries. Whereas in the lower figure, you have a lot of entries free and you can add more entries into the write buffer. So the write back from the write buffer is done when the write buffer is full most of the time. So you can actually, reduce the number of write backs by merging the entries in the write buffer if they are of contiguous address space. That is what this optimization does to reduce miss penalty. Okay. Any questions on that?
Ma'am?
Yeah.
Ma'am, like, will the second image work, or will the second image be implemented only when we have to store in continuous memory spaces, or
Yes. Otherwise they cannot merge because the address which you put on the address bus, you're saying now 100, right? And then you are saying, specifying how many bytes you are writing, or you are just putting the number of bytes in the data bus. So that many bytes will get written automatically into the memory starting at the address location that you have specified. If they are not contiguous, then they'll be writing into wrong location.
Okay. So,
So it's
do
a
they?
possibility.
So
If
they.
you have contiguous memory, you can do this and actually reduce your miss penalty. If it's not contiguous, you can't do. But because of the locality issue, most of the time you will be writing to contiguous memory locations, right? I mean, like you'll be writing to arrays a lot of time. And so this can be taken advantage of.
Okay.
I think you were asking something. I'm sorry, I spoke over you.
No, I got that. Like, so
Okay.
even if we have 3 continuous memory, we can use this. Like, if
Yes. As long as you have contiguous memory, you can merge and use, make use of more efficient space utilization of the write buffer.
Okay.
So pipeline caches. This was the question which was asked, that it's not clear. Now, let's go back again to the question I asked in the last class. What are the steps in the cache lookup? You index into the cache, right? Then you do, if you are using virtual indexing, physical tagging, you can do indexing into the cache while doing translation from virtual to physical address of the tag. Okay. After that, you have to match the tags. Okay. Once the tag is matched, you have to use the offset to, access the specific word or byte you're accessing, right? So these are the various steps that are involved in the access of the cache. Now, what is the point is that the clock cycle of the processors has become very, very fast, right? The processors are very fast despite attempts to close the gap between the processor and memory. It's become difficult to access the cache in one single clock cycle when the cache, processors have become so fast with such fast clock cycles. Now, the only way you can solve that problem is to reduce the clock rate of the processor, right? Because you would like, when we go into pipelining, I know I'm doing this in the reverse way, maybe partially. That's why Hennessy and Patterson do keep referring to pipelining in the chapters on memory, but I think I asked you people last time whether you did pipelining in your COA course. I didn't get any answer. If you know something about pipelining, then it's easy for me to explain from that perspective. Anyway, the point is that when cache access cannot be done in a single clock cycle of a very fast processor, there are 2 options that you are left with. One is to reduce the clock speed of the processor to match the speed of the cache. So your clock rate will be, such that every clock cycle you can access the cache. So that is one way, which is basically saying I'm going to reduce the speed of the processor. Another way is to say, okay, I'll pipeline the access to the cache itself, right? So what is pipelining? It's basically, you divide the job into multiple sub actions. So you have you basically have a task. You divide the task into subtasks such that each subtask is independently doable. Then what you can do is, while one person is doing one task, another person can proceed with another task on another data item. So you are basically parallelizing the work. So, it's something like you are cooking, somebody is, cleaning the vegetable, somebody is, peeling the vegetable, another is cutting the vegetable, and so on. Then you can actually, if you have 3 people, you can have 3 of them do the 3 different jobs. One person washes it, gives it to the person who peels it, and who passes it on to the person who cuts it. So this is pipeline. And this sort of pipelining can be done with the cache access. So what do? In the first cycle, you basically, you can do address translation, okay? Then using the, the tag bits, in the second cycle, you can pass it for tag matching, okay? And index also into the cache at the same time. In the third cycle, if there is a tag match, you go for accessing the specific word. So now instead of doing all of these things in one single cycle, which is what we have been assuming so far, we will actually, be doing each of them in a different cycle. Even though now, if you look at it, one single instruction fetch from the cache takes 3 cycles. But as we will see in the next chapter, pipelining chapter, what we will improve is the throughput. Okay, the latency for any specific instruction is not reduced. What is latency? When was it issued and when was it completed? So it's taking 3 cycles to look up the cache, whether you do this in a normal way or in a pipelined way. But after the first instruction is issued to the cache, the second instruction is not going to take 3 cycles because, as the first instruction moves from translation of address to indexing and tag matching of the address, the second issue from the processor will be actually doing the translation of the address. So you are, basically increasing the throughput of the cache instruction or data fetch. We are not reducing latency, but we are increasing the throughput. So the very first instruction will take 3 cycles before the processor can proceed. So the processor will have to stall for 2 cycles. But next instruction or data fetch onwards, the processor will not have to, stall because it's going to get 1 instruction or data item per cycle after that. That is the idea behind pipeline caches. Any questions on that? Yes, the pipelining will be definitely having a bottleneck based on the slowest element in the pipeline. So usually they try very hard to ensure that every stage in the pipeline is of equal length, as equal length as possible. In the case of our hardware architecture, I mean, like when you're talking about computer architectures, every stage will be once, based on number of cycles it takes. You would like every stage to take only 1 clock cycle, because then, every clock cycle, every instruction moves forward to the next stage. So you have an ideal pipeline where every cycle you will get 1 instruction completed. Okay, and the clock cycles per instruction will, basically tend to be 1. Clock cycles per instruction, if you remember, ma'am talked about in the first chapter. So that ideal CPI in the pipeline is that every clock cycle you will get a instruction completed. So yes, a lot of questions come up when we do pipelining. Therefore, how do you ensure that they are of equal length, or how do you handle when there are problems, and what sort of problems can come up? How do you overcome them? So all those questions we'll answer in the pipelining chapter. Any other questions? Actually, increasing penalty because you're saying it's taking a lot of time to write back more words now before it can write back, possibly. The point is that, if you're writing, let us say, 8 bytes of data to the memory, back to the memory, okay, versus you're writing back 64 bytes to the memory, okay. Now, the time taken to write back 64 bytes of memory, you have to do anyway, right? At some point, you have to write back 64 bytes of memory. So the time taken to write 64 bytes cannot be reduced by anyone, okay. What can be done is, if you have to write 8 bytes, 8 bytes, 8 bytes, like that 8 times, then you have to put 8 addresses on the address bus and then put 8 bytes on the data bus, okay? And then come back again and put another address on the address bus and another 8 bytes of data on the data bus. Now, every time you try to access the bus, please remember, bus is a broadcast element, right? So different elements of your architecture will be trying to access the bus. Therefore, there will be contention. And when there is contention, you have to probably wait before you can, access it. So accessing it 8 times for the address bus and 8 times for the data bus would still be involving a lot of latency. What is happening with merge buffers? You are putting the address once and writing the 64 bytes at once. So because you can't reduce anyway the time taken to write back 64 bytes, what you're reducing is the time taken to access the buses. That is one part of the answer. The second part of the answer is, please note that when we say there is a write back from the write buffer, this is happening in parallel with processor continuing to execute instructions. So unless there is a miss for something, the processor is not going to be affected by the fact that we are writing back from the write buffer to the main memory. So the penalty, whatever penalty we may incur from writing back from the write buffer to the memory, is not seen by the processor. And that's what is important for us. The whole of this story is the processor is far faster than the memory. Therefore, how do you ensure that the processor doesn't have to wait for the memory? So the write back happens in the background from the write buffer to the memory, but even there, we can reduce the amount of time taken by doing the merging. Does that answer your question? Okay. Anything about pipeline processor, pipeline caches too, if somebody is still not clear? Multi-bank caches, if you remember Bhaskar and Raman's third video, consists of increasing bandwidth for the memory, which is what this is. So, if you have to if you had to get, supposing let us say that you wanted to get a 4-byte value, let us say, okay? What is the multi-bank cache? How is it going to help? right? So if you want to get 4 bytes from the memory, from the cache, you'll put the address on the address bus from where you want that data, and 4 bytes will be read. Okay. Now, the thing is that if you can actually read all 4 bytes simultaneously, it will be really nice. Okay, of course, 4 bytes is a bad example because, you know, the processor, the memory anyway reads words at a time, sort of a thing, right? Most of the time, the memory may be word addressing, in which case it is going to read one word at a time. Even if you want 1 byte, you have to do whatever you have to do to, you know, do the shifting in the register and sign extend the value and so on. Okay, that problem will be there when you are talking about word addressable processors. But let's just take an example of a byte addressable processor. So you want to read 4 bytes. Okay, so you put first byte address on the bus, read the first byte, then the second byte's address on the bus and read the second byte and so on. So you have 4 accesses that are happening to the memory, to the cache. Now, instead of that, supposing you put one address on the bus, okay, and you have this multi-banked cache where you basically put an address of 0. All right, you put an address of 0 on the address bus, which will access the 0th byte or the very first byte in all the 4 banks of the cache. Okay, so it basically it's going to access this element in this bank, this element in this bank, this element in this bank, and this element in this bank. By putting a single address on the address bus and having lines basically, you know, having your address bus going like this, right? And you have an address 0 going on this, right? And you have this, you know, going to wherever you want to. So now by putting the address 0, it's going to address the 0th byte in all the banks. So all 4 of them will look up that entry in parallel, and then of course there is this bus contention, right? Because they're all trying to write to the same bus. But that bus contention is not going to be a very long delay. First, whoever wins the race will write their value, byte value onto the bus, it will be passed. Second, whoever wins the race will write that onto the bus and that will be passed and so on. So you, by passing one single address and in parallel, you are able to extract the data from 4 different banks by doing this. So there is a parallel lookup and parallel read. There is a parallel read, which is what reduces the time taken. So this increases the bandwidth. So here we are assuming that our address bus is 8 bits, right? Because I said each of them is bytes. So we are assuming our address bus is 8 bits, but we are able to read 32 bits in one read by doing this sort of parallel reading. Okay, so that is multi-banked caches. Any questions on that?
Ma'am?
Yeah.
Um,
I think we'll be running out of time in another 2 minutes. Yeah.
Okay. Ma'am, let's say I want to read the first byte in bank 1. And I want the data from the bank 1.
Okay.
So the processor should send 0.
Yes.
And when it gets the data, how can it differentiate between each of them? Like,
Basically, it will have some sort of, you know, the block address will now probably consist of bank information also.
okay.
From which bank it came. So it's like, it can be part of the block address, it can be additional bits which probably come back,
Okay.
which tells you who won the bus, right? Because even if you don't want to read the 3 bytes of the other banks, or you may be trying to read, you issue this read and you issue a read to some block, 2 in bank 3, something like that. Then you have to make the different, be able to differentiate between these.
Yeah.
But the main, let me put it this way, the main advantage they usually gain from this is you want to read what is called as a wide word. Okay. The word is 4 bytes, but a wide word is 4 into 4, 16 bytes sort of a thing. Then you can actually read so many of them at one shot by putting one single address on the bus. So it increases the bandwidth of, it increases the bandwidth of how much you can access at one single read access. So, I mean, if you want to read only one, you're allowed to do so. But by the way you interleave it, and if you see, that's what they do. 0, 1, 2, 3 are different, interleaved in different banks. So they are contiguous bytes. You want to read one word, you put the address 0 on the bus, you will get 4 bytes, which together represent one